Today, we're cracking open one of the biggest cold cases in the history of science. It's a cosmic detective story, and it gets to the very heart of a question that sounds simple, but is anything but. Why does our universe even exist?
I mean, really think about that. Why is there something here? Because according to everything we know about the beginning of time, the universe should be totally empty. All the stuff that makes up you, me, this planet, all of it should have just vanished in a flash of light. So, what went wrong? Or, I guess, what went right?
Okay, so here's the deal. The Big Bang should have cooked up matter and its perfect opposite, antimatter, in exactly equal amounts. Now, the one thing you need to know about antimatter is that when it touches regular matter, poof, they annihilate each other, leaving behind nothing but pure energy. So, if you start with a perfect balance, you should end with a perfect cancellation, leaving, well, nothing. And yet, look around. We're here. The universe is here. Something survived.
For decades, physicists have been like cosmic detectives, hunting for a clue, any clue, that could explain this survival. And very recently, they found one. A brand new, incredibly complicated, and super fleeting particle that might just be a crucial piece of evidence in this whole investigation.
Get ready for this name. It's called Antihyperhydrogen-4. Yeah, it's a mouthful, but this thing is, by a huge margin, the most complex and heaviest chunk of antimatter we have ever managed to create and actually study. Just being able to make it is a massive achievement, and locked inside it are clues to the universe's deepest secrets. So what in the world is this thing? Let's peel it back like an onion. Layer 1 is pretty simple. It has one antiproton, which basically makes it a type of antihydrogen. Layer 2 makes it a bit heavier. It's got two antineutrons hanging around. But layer 3, oh, this is the really wild part. It contains an exotic particle called an anti-lambda hyperon. And this gives it a special property that physicists with a bit of a flair literally call strangeness.
And if we zoom in even further down to its fundamental building blocks, it gets even crazier. This one particle is actually a little bundle of 12 antiquarks, and that includes the one special anti-strange quark that gives it its name. It's this unique, complex recipe that makes it the perfect tool for stress testing the laws of physics.
Right, so you can't just find a particle like this kicking around in nature. To get your hands on this clue, you have to build a kind of time machine, a cosmic crime lab, powerful enough to wind back the clock and recreate the fiery conditions of the universe just moments after the Big Bang itself.
So inside this incredible machine called the Relativistic Heavy Ion Collider, scientists create a mini Big Bang. And they do it by taking gold ions and smashing them together at, get this, 99.9% the speed of light. The collision creates this trillion-degree soup called a quark-gluon plasma, which is the exact same primordial gunk that filled the entire universe in its first few moments. Then, for just a tiny fraction of a second, as the soup cools, the right antiquarks can find each other and clump together to form our ghost particle.
Now, just try to wrap your head around the scale of this search. The team had to sift through the data from 6.6 billion high-energy collisions. That is the very definition of looking for a needle in a haystack.
And the needle they were looking for? It's a true ghost. It exists for about 0.1 nanoseconds. That's a tenth of a billionth of a second. It's gone before you can even process that it was there.
So, after analyzing 6.6 billion collisions, hunting for a particle that lasts for a tenth of a billionth of a second, how many did they find? 16. That's it, just 16. Each one of those is an unbelievably precious clue.
So how do you even prove something existed if it disappears that fast? Well, it's pure forensic science. See, the parent particle, our ghost, decays into two more stable daughter particles. The scientists, our detectives, can see the tracks these daughters leave behind. And what they do is trace those paths backward. If the paths meet up at a single, precise point in space, that's the smoking gun. That's the proof that the parent particle was right there.
Okay, so our detectives found their clue. They proved it was at the scene of the crime. The next big question is, what did this piece of evidence actually tell them? What's the final verdict on the fundamental laws that govern our universe?
This whole massive experiment was designed to test one of the most fundamental rules in all of physics, something called CPT symmetry. Now, put simply, this rule says that the universe is supposed to be perfectly symmetrical. If you take a particle, flip its charge, look at it in a mirror, and run its life in reverse, it should obey the exact same laws of physics as its regular matter twin. It's supposed to be the ultimate cosmic mirror.
So, the moment of truth.
They measured the lifetime of their 16 ghost particles, and what did they find? They discovered that Antihyperhydrogen-4 lived for the exact same amount of time as its regular matter version. The verdict came in. CPT symmetry holds up. The cosmic mirror isn't cracked. The law, as we know it, is perfect.
And this is where the story takes a wild turn. Because this verdict doesn't solve the case at all, it actually makes the mystery even deeper. If the laws of physics really do treat matter and antimatter as perfect mirror images, then we still have no explanation for why one completely took over the universe. We're back to square one, but now we're even more puzzled.
But hang on. Just because the main case is still wide open, it doesn't mean our new clue was a dead end. Not at all. In fact, this discovery is already helping physicists crack other massive cosmic puzzles.
For starters, studying how this strange particle is held together gives us clues about the cores of neutron stars, those incredibly dense objects left over when stars die. It's helping us figure out why they don't just collapse into black holes. It also gives a crucial baseline for experiments hunting for dark matter. Now that scientists know exactly what this heavy antimatter looks like when it pops up, they won't accidentally mistake it for a signal from something even more bizarre.
And this table really just nails how huge of a leap this is. Compare it to a simple antiproton, something we've known about since the 50s. Our new particle is way more complex. It has that strangeness quality, and its whole purpose isn't for something like medical imaging, it's for testing the very fabric of reality itself.
You know, one of the researchers said it best. This is, hands down, the most complex piece of the antimatter puzzle ever assembled. Think about that. We recreated the birth of the universe to forge a particle that hasn't existed for over 13 billion years, all just so we could ask the biggest questions we can possibly imagine.
So, we end up here. This amazing ghost particle has confirmed that the rules of the game, the laws of physics as we know them, are incredibly solid. But that just means the real answer to why we exist must be hiding somewhere else. It must be in some new physics, some new rules we haven't even discovered yet. The case of the missing antimatter isn't closed. A new clue just blew it wide open.